Hi guys, I'm back with the fourth video, which is on separations. So yeah, there are many kinds of separation. Some of them are listed here: liquid extraction, crystallization, leaching, stripping, rectification, distillation, absorption, chromatography, membrane absorption. There are many of these, and most of them you must have heard of. So let's discuss some of them. One is distillation. As it says, distillation is depending on volatility. Some people say that depends on boiling point, but that is not actually correct. So volatility is a better term because boiling points change in, let's say, azeotrope or something. Yeah, so that is one thing. So you say volatility and not boiling point. So yeah, let's say in distillation. Okay, so we take a mixture A plus B, which are different to volatile, and then you have trace. So yeah, many trades. Big distillation columns are of the order of 90 meters length. Yeah, so what there's a vapor coming out of here, and then you have a condenser, and then this separate to two streams, and this is called what comes out is called overhead. What goes back is called efflux, and then you have one thing over here on the bottom. A liquid comes down. Then, as you see, this is vapor coming up. This is a liquid coming down. Yeah. So this is heat is given in. Here heat is taken out. So this is a liquid now. The vapor is condensed into a liquid. Here there is a liquid which is boiled. So what goes back is called boil up. What comes out is called bottom spread. Okay, there is one small important point that you must keep in your mind that when the vapor is coming here, the complete thing is being liquidized or complete thing is being condensed. So the composition of overhead and the composition of reflux are always the same. And second thing, when you are considering the bottoms, the liquid is boiled and there is boil up in bottoms. So the composition need not be same. Actually, in general, the composition is not the same. Yeah, so that was about some terms. Then we have some laws. One is called Raoult's law. Please check the spelling. I'm not sure about the spelling. Okay, Raoult's law. There's some O somewhere, I guess. Okay, so what does Raoult's law say? It says yi into pt equals to xi into vp of I. So what does this say? It says that let's say let's say there's a gas liquid system. There's a liquid and there's a gas. Okay. So in the gas, let's say there are components A, B, and the liquid there are components A, B. There may be some components which are in gas but not in liquid. So let's assume that as well. So pressure total is partial pressure of A plus partial pressure of B plus partial pressure of C. So and partial pressure of A can be written as Yi into partial total pressure. That is what the left term means. And the right term is Xi is the mole fraction in liquid. So one thing you need to keep in mind that Xi in general is not equal to Yi, and yeah, so mole fraction in liquid into vapor pressure at that temperature. So this is again given by Antoine equation. If you remember, I had discussed in one of my videos that log Vp equals to A minus B by T plus C. So this gives the vapor pressure. Yeah, so this is the general thing, but this one thing you need to keep in mind that Raoult's law is only applicable in equilibrium case. If the equilibrium is not maintained, maybe there is no liquid and the gas is and there's only gas, there is no liquid. In that case, this does not hold. So let's say you have water and air. equilibrium, so you'll have xi is equal to 1 because there's only water, but y is not equal to 1. In that case, y is not equal to 1 because you have some oxygen, some nitrogen, which are not in liquids but are only in gases, and then you have water vapor. So y is not equal to 1. In that case, you'll get partial pressure of water is equal to 1 into vapor pressure of water. So that's what we generally say, that when water is in equilibrium with air, so the partial pressure of water in air is equal to its vapor pressure. And when this vapor pressure reaches 1 atmosphere or atmospheric pressure, that condition is called boiling. Okay, this is some small point, but anyways, so whenever liquid is in equilibrium, when a single component liquid is in equilibrium with the gas, you would say that the partial pressure of that liquid is equal to vapor pressure of that liquid. Okay, now we come to another point. It is called bubble point and dew point. So basically, bubble point, you have a liquid, a complete liquid. There is not a single mole of gas, not a single millimole of gas inside it. So this is a complete liquid, and you keep on heating it, keep on heating it, keep on heating it. You keep on heating it. So the minimum temperature at which the first gas bubble forms, that is called a bubble point. So yeah, the word bubble suits there. And then for dew point, yeah, this one thing is to be kept in mind, that pressure is constant when we are considering this. Yeah, so the this is the temperature for first bubble, and then here you have full gas, not a single drop of liquid, and then you keep on cooling it, and the maximum temperature, T max, for the first drop, this T max is called dew point. So you should be clear that T min for the first bubble is bubble point, T max for the first drop is dew point. Okay. Now let's talk about some interesting thing. It's just the graph. Sorry, it's not a rectangle, but yeah, okay. Bear with me. So here you can denote both XA and YA, where A is some component starting from 0 to 1, and on the y-axis I'm having temperature. Fine. So let's consider some point here. So this is when X is 0, Y is 0, and then which is pure component B. Then you draw a line. This is XB. Yeah, this is XB equals to 1, YB equals to 1, which is pure. Sorry, XA equals to 1, Y equals to 1, which is pure A. So you get a graph something like this. Okay. So this region is a complete liquid region. Completely liquid region. This is a completely gas region. And here in this region you are getting gas liquid equilibrium. Okay. Now how to read this? Let's say I am at a particular temperature. So what I do is I draw a horizontal line at that temperature. Okay, my line is ready. Now wherever it intersects first, that I drop down. Where it intersects later, I drop it down again. So now if you would have seen that, let's go back to Raoult's law. Y into Pt equals to Xa into vapor pressure. Okay, so let's do some manipulation. Ya by Xa equals to Vp by Pt. Now we know that Vp is 100% less than Pt, right? So we can say Y will be less than Xa. So the one which is going to come later is Xa. One which will come first is Ya. That is one thing. Now, what is this Y and what is this Xa? So if there's a system, you have liquid, you have gas of A plus B, then this is liquid, this is gas, of course, then the composition here is XA and the composition here is YA. So that is given from this graph. And for a given XA, these this above line, so you see this is gas, then you keep on cooling down, and at a point you will cross this, you'll come to gas liquid equilibrium, which means that on the above line you are getting the first drop. So the above line represents dew points. Similarly, the below line will represent bubble points. Okay, so that's all about dew point and bubble point. You can draw maybe one more graph like this. Okay, again not straight, but okay. So yeah, it does not count. This is y versus x. That's the graph you may see, so don't get confused. Yeah, this is y versus x. It will be either above the line or below the line, and if the gases are non-ideal, it will somewhat go and cross like this. But anyway, we are not discussing the non-ideal case, but just keep in mind that how the graph of y versus x looks. Okay, and then we have gas liquid equilibrium. This was whenever liquid is going into vapor form, it is called liquid and vapor. Gas means a thing in gaseous state which cannot be converted to liquid by merely dropping down, increasing the pressure. So yeah, so there is a very small difference between gas and vapor. So yeah, when you say gas liquid equilibrium, it means that how much is the solubility of the gas in the liquid. Let's say you have oxygen, how much oxygen is getting dissolved into liquid. So you say partial pressure of oxygen is some constant times vapor pressure of water. Anyway, like there is some equation like this which you don't need to worry, but yeah, there is a law which defines this solubility, and it is called Henry's law. Okay, now again, like you had the graph for dew point, bubble point. You have a graph for crystallization. This time I'll try to draw a straight box. Yeah, more or less successful. Anyway, so not so straight, little bit bent. Yes, somewhat like this. This is the solubility curve, and we are talking about crystallization. So on the y-axis you have solubility, on the x-axis you have temperature. What can you read from this graph? So as you know, when you increase the temperature, solubility increases, which is directly evident from this graph. Let's say you're in this region. Yeah, so this is the saturation line. This is the saturation line. This is oversaturated, which means it won't exist. This region you can't go, and this is undersaturated region. So yeah, let's say you are at some point over here, and what do? You increase the temperature. Let's say you increase the temperature, but you keep the concentration same, so you keep on going here, which means it will be dissolved inside. There is no worries. But then what to do if you start decreasing the temperature at this point? So from here you'll go here first. Let's say you reach this point here, you reach this point over here. Now what to do? You cannot go into this region as it is prohibited. So if I decrease the temperature further, what will happen? It will travel along this line. It will travel along the curve. It will reach here. That's so initial point was this, final point is this. Let's draw a line. This difference is the one which has come out of the solution. All of this has come out of the solution. In other words, this is all that is crystallized. See, because if you are going here, It is not possible. So you need to travel along this curve. So the solubility is decreasing. So where's the remaining salt going? It is going out of the water or out of the solvent. So that's all. So that is the amount which is crystallized. So now you can read a solubility curve. Now let's talk about something called Gibbs phase rule. A very simple rule, but very interesting. It says P plus F is C plus 2. P is phases, F is freedom, which means degrees of freedom, C is components. So let's say you have water, only one component, and liquid. In this, liquid and vapor in equilibrium. Okay, so number of phases is 2, number of degrees of freedom I don't know, components 1 plus 2, so which gives me F equals to 1. So given that what liquid and vapor are in equilibrium, sorry about this, I think I need to stop early. But anyway, I'll complete this. Given that liquid and vapor are in equilibrium, there's only 1 degree of freedom, which means you can set either the temperature or you can set the pressure. In general, degrees of freedom include xi, yi, and T and P. So, if the degree of freedom is 2, you can set any two of these, and the others will get set according to vapor pressure Antoine equation or according to Raoult's law. Other things will get set. So yeah, here if you set temperature, the pressure will get set according to the Antoine equation. Yeah. So generally, I forget that which thing comes on which side. So the best idea to remember this is consider triple point of water. You know that triple point of water is uniquely specified. It cannot change. You cannot do anything with that. You don't have any freedom. So degree